This video explains concurrency control and locking concept in the most simplest way possible. So let's go. Concurrency means multiple transactions accessing the database at the same time. The simultaneous access can create problems. For example, as shown in the illustration, transaction 1 and 2 are both trying to access the database at the same time, which does not augur well for a database in any sense. Practical example is when two multiple transaction access bank account simultaneously. If this concurrency is not handled properly, it can create havoc in database, leading to incorrect balances and data inconsistency, which indeed is a problem. See, concurrency can cause serious problems, and that's where concurrency control comes in. It mainly prevents lost updates, non-repeatable reads, and phantom reads. In this video, we will break down each one step by step. First, look at the lost update problem. A lost update happens when one transaction overwrites the update made by another transaction. It sounds tricky, but it's easy to understand with example. Suppose a bank account 101 has a balance of 1000 rupees. Now two transactions happens at the same time. Transaction 1 wants to withdraw 200 and transaction 2 wants to deposit 300. Here's what happens. Both transactions read that the initial balance of 1000 at the same time. Transaction 1 subtract 200, updating the balance to 800. Meanwhile, transaction 2 also reads 1000 and adds 300. This ignores the withdrawal that already happened, so the final balance becomes 1300 instead of correct 1100. This is the lost update problem. One transaction's update gets lost because the transaction happened concurrently without proper control. The second problem is non-repeatable action. This happens when a transaction reads the same data twice and gets different values because another transaction changed it in between. Let's see a simple example. Imagine a product, say chocolate, priced at 100 rupees. Transaction T1 is done by a customer who checks the price and sees 100. Meanwhile, transaction 2 done by the shopkeeper or admin updates the price to 120 and commits it. When the same customer checks again, the price is now 120 instead of 100. This is non-repeatable read. The same row was read twice but gave different values because of concurrent transaction. This happens when a new row appears in the result of the same query executed twice within a transaction. Let's take an example of order table. Suppose there are two orders, order 1 for 500 and order 2 for 1500. Transaction T1 is done by a manager who wants to see expensive orders above than 1000. The first time T1 runs the query, only order 2 appears. Meanwhile, transaction 2 done by a customer places a new order 3 for 2000. When the manager runs the same query again, now the two order appears, order 2 and order 3. This sudden appearance of a new row is called phantom read. A new row shows up between two reads of the same query because another concurrent transaction had happened in between. So these are the kind of problems concurrency can create in database, effectively causing havoc to database. What's the solution then? There are two main approaches, pessimistic and optimistic concurrency control. In the pessimistic approach, we assume conflicts are likely, so we lock the data before a transaction starts and don't allow the other transactions to interfere until the first one is done. There are two types of locks, shared lock for reading and exclusive lock for reading and writing. In optimistic concurrency control, we assume conflicts are rare. Transactions are allowed to run simultaneously without preset locks. The process involves 3 steps: read, validate before commit, and then commit. And if there's any conflict, we retry. If not, it proceeds. The approach is lighter than pessimistic locking and also more efficient in terms of database usage. So in the pessimistic approach, which is used more often in database administration, we create locks to prevent conflicts, as we discussed earlier. There are two types of locks, shared and exclusive lock. A shared lock allows read only access, while an exclusive lock allows both reading and writing. Looking at the illustration, let's assume T1 and T1 is transaction 1, S is the shared lock on the data A, where R is read and U is unlock. For any transaction to release lock, it must unlock the data. Until it does, other transactions cannot access it. This ensures data consistency and prevents conflicts. Similarly, we have the exclusive lock for transactions like transaction T2 working on data B. For an exclusive lock, we mark it with X followed by the data being accessed. The transaction can read and write the data. Once the work is done, we unlock the data. So this is how the shared and exclusive locks work to control access and maintain data consistency in the database. Now that we have learned about shared and exclusive locks, let's move to the real deal. Two-phase locking, a key concept in database concurrency control. Two-phase locking has two phases, as we can see from the name: the growing phase and the shrinking phase. In the growing phase, a transaction acquires all the locks it needs. Then comes to shrinking phase, where the locks are released so the other transaction can access the data. There's also a transition part in between where the transactions move from growing to shrinking phase. Before we dive deeper, let's check the compatibility table. There are four possible locks combinations: shared, shared, shared exclusive, exclusive shared, and exclusive exclusive. Only shared allows transactions to run simultaneously. For the other combination, transaction must wait until the lock is released. For example, transaction 1 locks the data A with the exclusive lock because it needs to read and write. At the same time, transaction 2 requests a shared lock on A. It cannot proceed until transaction 1 releases the lock. Transaction 1 then acquires a lock on data B, reads it, and finally unlocks A and B. After that, can transaction 2 proceeds with its operations. This ensures data consistency and prevents conflicts with multiple transactions and concurrency. Now let's look at the diagrammatic view of the two-phase locking. In this diagram, you can see a graph that goes up and then down. This represents the growing and shrinking phases. It starts at a point 1, then at point 2 and 3. It requires two locks. The transition phase happens in between growing and shrinking phases. Point 4 and 5 represent the unlocking phases, and point 8 marks the end of the transition. This diagram shows two locks, but you could have 3, 4, 5 or more locks in transition. There's no restrict or limit to transitions. For example, in transition T1, a shared lock on A reads A, then acquires an exclusive lock on B, reads B, then writes B, and finally unlocks A and B both. This is the written representation of the diagram above. Thank you so much for watching. I hope this video helps you understand and solve concurrency control problems. If you have any questions or topics you want me to cover in future videos, drop them in the comments. I'll be happy to make more videos for you. Thank you.